SCAP is a suite of open standards developed by the National Institute of Standards and Technology, NIST, that enables automated vulnerability management, measurement, and policy compliance evaluation. SCAP isn't a single technology or tool, but rather a collection of interoperable specifications that work together to provide standardized methods for maintaining system security. These specifications enable organizations to automate security compliance checking, vulnerability assessment, and configuration management at scale. The protocol addresses a critical challenge in cybersecurity: how to consistently and efficiently assess security posture across diverse IT environments containing different operating systems, applications, and network devices. SCAP emerged from the need to standardize security automation across government and enterprise environments. Before SCAP, organizations struggled with inconsistent vulnerability scanners, incompatible security tools, and manual compliance processes that were time intensive and prone to errors. SCAP provides a common language and framework that enables different security tools to share information and work together effectively. This standardization is particularly important in large organizations where multiple security products must integrate seamlessly to provide comprehensive coverage. SCAP consists of several key component specifications that work together to enable security automation. Each SCAP component serves a specific purpose in the overall framework. Common Vulnerabilities and Exposures (CVE) provides unique identifiers for publicly known vulnerabilities, ensuring that different tools and databases can reference the same security issues consistently. Common Configuration Enumeration (CCE) offers similar standardization for configuration problems, giving each type of misconfiguration a unique identifier that tools can recognize universally. Common Platform Enumeration (CPE) creates a standardized naming scheme for IT platforms, operating systems, and applications, enabling tools to accurately identify what systems they are scanning. Common Weakness Enumeration (CWE) classifies the underlying weaknesses that lead to vulnerabilities, helping organizations understand root causes of security issues. Common Vulnerability Scoring System (CVSS) provides a standardized method for rating vulnerability severity, ensuring consistent risk assessments across different tools and organizations. Extensible Configuration Checklist Description Format (XCCDF) creates digital security checklist that defines exactly what security settings should be configured on systems, allowing automated tools to verify compliance instead of requiring manual checks. Open Vulnerability and Assessment Language (OVL) provides a comprehensive language for describing system characteristics, vulnerabilities, and configuration states in a format that automated tools can understand and act upon. The key strength of SCAP is how these specifications work together. The identification components CVE, CCE, CPE, and CWE establish a common vocabulary that all SCAP compliant tools understand. The assessment component CVSS provides consistent risk evaluation methods that organizations can rely on prioritizing remediation efforts. The implementation components XCCDF and OVL translate security policies and requirements into machine readable formats that enable automated compliance checking and vulnerability assessment. This integration means that security findings from one SCAP compliant tool can be understood and processed by another, creating an interoperable ecosystem of security automation tools. Now let's examine how SCAP operates in real world environments. In practice, SCAP implementation begins with content creation, where security professionals define organizational policies and requirements using XCCDF checklist and OVAL definitions. These documents specify exactly what configuration should be present and what vulnerabilities should be absent from systems. During system discovery, SCAP tools identify target systems using CPE naming conventions, ensuring accurate system identification regardless of the specific scanning tool being used. Assessment execution involves automated scans that check systems against the defined policies, looking for vulnerabilities, misconfigurations, and policy violations. Results collection standardizes all findings using CVE identifiers for vulnerabilities and CCE identifiers for configuration issues, ensuring consistency across different tools and time periods. Risk analysis leverages CVSS scores to help security teams prioritize which issues need immediate attention versus those that can be addressed in routine maintenance cycles. Compliance reporting generates standardized reports that clearly show security posture and compliance status in formats that both technical teams and executive management can understand. In enterprise environments, SCAP deployment centers around centralized policy management, where security teams create and maintain XCCDF checklists that define organizational security requirements and compliance standards. These policies are then distributed to scanning tools throughout the infrastructure for distributed scanning, where SCAP compliant vulnerability scanners and configuration assessment tools perform automated evaluations across servers, workstations, and network devices. Standardized reporting aggregates results using common identifiers and formats, enabling security teams to view consolidated information regardless of which specific tool performed the assessment. Perhaps most importantly, SCAP's standardized data formats enable seamless integration with security tools, including SIEM systems, governance, risk, and compliance platforms, and vulnerability management solutions, creating a unified security ecosystem where information flows efficiently between different tools and teams. SCAP provides significant benefits for organizations implementing security automation programs. SCAP standardization eliminates the confusion that occurs when different security tools use incompatible data formats or inconsistent vulnerability identifiers. Organizations can confidently compare results from different vendors and time periods, knowing they're working with consistent, reliable data. Automation capabilities significantly reduce the manual effort required for compliance checking and vulnerability assessment, freeing security professionals to focus on higher value activities like threat hunting and security architecture. Interoperability ensures that investments in security tools provide maximum value, as different products can share information effectively without requiring custom integration work. This leads to cost efficiency through reduced vendor lock in and improved tool integration, allowing organizations to select best of breed solutions rather than being constrained to a single vendor ecosystems. Compliance support streamlines adherence to government regulations and industry standards that increasingly require SCAP compliant reporting. The accuracy improvements from standardized automated assessments reduce human error in security evaluations, while scalability enables efficient security management across large, diverse environments that would be impractical to assess manually. Organizations with government requirements find SCAP essential, as federal agencies and government contractors often have specific mandates for SCAP compliant vulnerability management and compliance reporting. Those managing complex environments with diverse operating systems, applications, and network devices benefit tremendously from SCAP's standardization, which provides consistent security assessment across heterogeneous infrastructures. Organizations seeking to integrate multiple security tools discover that SCAP enables these platforms to work together effectively, sharing vulnerability data, configuration information, and compliance status seamlessly. Any organization needing to demonstrate compliance finds that SCAP's standardized reporting formats support audit requirements and regulatory compliance much more efficiently than custom or proprietary reporting approaches. Understanding SCAP versions and compliance requirements is important for certification preparation and professional implementation. SCAP version evolution reflects the changing needs of cybersecurity and IT environments. SCAP 1.0, released in 2009, established the foundational framework and proved the concept of standardized security automation. SCAP 1.1 enhanced these capabilities with broader tool support and improved interoperability between different vendor products. SCAP 1.2 includes improved specifications, that address lessons learned from early implementations and provide better support for complex enterprise environments. SCAP 1.3, the latest version, incorporates enhanced automation capabilities and improved support for cloud environments, reflecting the modern shift towards cloud computing and DevSecOps practices. SCAP compliance validation ensures that tools claiming SCAP support actually implement the specifications correctly. The NIST validation program provides official testing and certification, giving organizations confidence that validated tools will work as expected. Capabilities testing verifies that tools correctly implement all required SCAP specifications, while interoperability testing ensures these tools can effectively share data with other SCAP compliant products from different vendors. Content validation confirms that SCAP security checklist and OVAL definitions meet the technical specifications, ensuring that security policies can be reliably automated across different tools and environments. SCAP concepts frequently appear on cybersecurity certification exams. Certification exams commonly test component understanding, requiring candidates to know not just what each SCAP specification does, but how they work together to enable security automation. Implementation scenarios test practical knowledge of when and how to deploy SCAP solutions in different organizational contexts. Compliance requirements questions often focus on government mandates like FISMA or industry standards that require SCAP compliant vulnerability management. Tool integration concepts test understanding of how SCAP enables different security platforms to work together effectively. Finally, questions about benefits and limitations evaluate whether candidates understand both the advantages of SCAP adoption and the potential challenges organizations might face during implementation. To summarize, SCAP provides standardized frameworks for automated vulnerability management and compliance checking through its seven component specifications. It's particularly valuable for government contractors and large enterprises requiring consistent compliance reporting. I hope this overview helps you understand SCAP and its role in modern security automation. Thank you for watching, and I'll see you in the next cybersecurity video. Thanks.